Oh my. Here we are, about to begin a journey that for some of us, it may be quite quick. In fact, some of us may skip the journey altogether. For others of us, it may be a somewhat longer, lengthier journey. But again, right, it's not about the journey, it's about the destination. Or maybe it's actually the opposite. Maybe, maybe I said it wrong. Maybe it's not the destination, maybe it's the journey. I don't know, but just let me assure you, we're going to learn a lot, and we're going to have a lot of fun in the process as we make our way through the review material. So, right, Stat 512, as was probably told to you by your Stat 511 instructor, assumes a certain exposure to what could be considered kind of like a very basic, low-level, non-calculus based introductory sort of Stat 101 class. Here at Westchester University, we call it Math 121. And so the goal that I have with these PowerPoints, I think 12 in total, is to kind of give you a little bit of exposure to the material that I'm going to expect you to know as we start Stat 512, and hopefully give you some tools to learn it along the way if you have not already learned it. Of course, if you have learned it but it's rusty, these will be good review for you. If you have learned it recently, then you may just want to skip it its entirety. I would still encourage you to kind of actually pop open the PowerPoints. You don't have to listen to them. But if you've taken like a Math 121, Stat 101 course recently, you could probably just thumb through the slides and see how familiar they are or not familiar they are. And if some of them look a little bit unfamiliar, you can just listen to those slides and maybe do some of just those practice problems. It's intended to be self-guided. If you have any problems, if you find any errors along the way, then please let me know. Of course, it's too late for you, but we can still hopefully fix it for future generations. So with this disclaimer behind us, let's go ahead and plunge forward on our ever-exciting journey into the heart of statistics. So the goal of statistics is what? The goal of statistics, ultimately, the goal of the statistics is to determine information about a population. That is, we have some population that we're interested in, and we want to sort of figure something out, determine something, sleuth something about that population. It's the goal of not just statisticians, but most researchers. Now, statistically speaking, these are the types of things that we're often interested in. We're often interested in the population mean, right? The mean of a population, say the average salary for a particular profession. The population variance, the amount of variability in a particular population, or the population proportion P, right? Maybe the proportion of all Xboxes that are defective, or more abstractly, maybe the proportion of all surgeries that will be successful, which we might then use as a proxy for, right, the percent chance that any one surgery will be successful. Now note that under traditional statistics, under what's called kind of a frequentist viewpoint of statistics, these characteristics of interest are considered fixed, constant values. They're not random variables, they're not random, and we refer to them as parameters. That makes sense, right? They're attributes or characteristics of the population. Population starts with the letter P, so why not use something like parameters, which also starts with the letter P, right? P and P. It's a, what do they call that? Alliterative? It's alliteration. So how do we get this information? We get information about the population by taking a sample, right? Because the reality is, well, you might think it's a sad reality, but it's actually a quite exciting reality. The reality is that most populations are too large for us to look at in their entirety, which feels sad, but in a way is good for us, right? And it gives us some really exciting, fun, well-paying jobs. If we did live in a world where we had sort of unlimited resources, and we could, because of those unlimited resources, look at a population in its entirety, we would have no need for statistics. Statistics as a profession exists because we live in a world of limited resources, and in this world of limited resources, we don't have the time or the money or the man/woman power to actually look at all of the population. So we have to settle. We settle for looking at a part of that population. That part of a population is referred to as a sample. In Stat 514, you'll actually spend an entire course talking about kind of the ins and outs, the subtleties and intricacies of taking a sample, how you could take it well, how you could take it poorly. But for now, we'll just kind of think of this big picture idea of taking a sample, just looking at a part of that population. The most common type of sample is something referred to as a simple random sample, often abbreviated with SRS. We take a simple random sample of some arbitrary size n. So n is a very common placeholder for the size of our sample. N is in number of observations in our sample. And we use this sample to come up with our best guess for whatever parameter it is we're interested in. These best guesses based off our sample are called statistics. So again, the alliteration lives on, right? The attributes of our sample are referred to as statistics, S and S. The statistics that we're often interested in are the sample mean. So the sample mean we refer to with the symbol x bar. The sample variance we refer to with the symbol s squared. And the sample proportion we refer to with the letter p, that little caret on top of it, we call it a hat, so we would call this p hat. The sample mean x bar is our best guess for the unknown population parameter, the unknown population mean, which we represented with that Greek letter mu. The sample variance s squared is our best guess for the typically unknown population variance that we denoted in the previous slide with the Greek letter sigma squared. And the sample proportion, p hat, is our best guess for the generally unknown population proportion p. So this is kind of like the whole big idea of statistics, is how we use these things called statistics, these numbers generated from a sample to answer some question about our population. So big picture, we're using information in our sample to come up with information about our population. Now, the sort of beginning part of this process is often referred to as descriptive statistics. So descriptive statistics are kind of, we've taken a sample and we want to in some way sort of look at how we might describe what's going on in that sample. And there's sort of two types of descriptive statistics. There's graphical or visual descriptive statistics. That's actually what we're going to focus on, I think, for the remainder of this PowerPoint. And then there is numerical descriptive statistics. That's what we're going to focus on in the next PowerPoint. Now, graphical, visual descriptive statistics are actually pretty hot these days. You'll see the term data visualization. But that's just a fancy word for like visual descriptive statistics. I mean, don't get me wrong, they're doing some pretty cool stuff now that they weren't doing, say, even 2, 3, 4, 5 years ago, but the spirit is still kind of the same thing. Now, in both cases, both visual and numerical descriptive statistics, the appropriate one to use depends upon how we might characterize the variable that we're wanting to summarize or describe. And so the variable could sort of be characterized in one of two ways, at least one of two ways that we're going to focus on. The first is quantitative. So, right, a quantitative variable is a variable that's numeric in nature. So, right, the root word of quantitative is quantity. Quantity is an amount is a number. Now, if a variable is not numerical, then we're going to say it's qualitative. Qualitative variables are perhaps a little more commonly referred to, as categorical variables. So the type of descriptive statistics, and again, in this PowerPoint, we're focusing on visual or graphical descriptive statistics. So the type of graphs that we're going to do depends upon whether or not our variable is quantitative or qualitative, whether or not it's numerical or categorical. Yeah, and we mentioned this dichotomy here. We're going to focus on graphical now. We'll do numerical in the next PowerPoint. So so the basic graphical summaries that we would use for the different types of variables, for qualitative variables, probably some of the two most common ones are bar graphs and pie charts. I'm pretty confident we're familiar with both of those already. We see them in newspapers, we see them in say, popular magazines, right? Sports Illustrated, Time, Newsweek, all of these different magazines use bar graphs and pie charts to illustrate all sorts of different information. For quantitative variables, the graphs can get maybe a little bit fancier. We have histograms. We have stem and leaf plots. Stem and leaf plots are just fancier versions of histograms. And box plots. Now, I want us to focus on histograms because, right, like I said, the qualitative ones I like to think are pretty straightforward and don't need much talking up. And in terms of quantitative variables, probably the single most widely used and hence the single most important type of graphical summary is the histogram. Histograms are actually, we'll see, are a lot like bar graphs, right? So they just create a bunch of bars, and the bars are touching one another, and the height of the bar sort of represents how much of the sample falls into a particular category. We'll see some examples in just a little bit. Now, the primary use of histograms is to show us the shape of a distribution. Now, the typical shapes that we're looking for are skewed versus symmetric. So if something's not symmetric, we say it's skewed. And there's two types of skew, left skew and right skew. We also sometimes look to see whether a histogram might be bimodal or whether or not a histogram might be uniform. Let's look at examples of these. So here's an example of a symmetric histogram. It also kind of has a little bit of what we might think of as like a classical bell shape. We'll talk more about bell-shaped distributions down the road. So a lot of standardized tests are man-made, are created by us specifically to follow a symmetric, often bell-shaped distribution. So the SAT score is an example of this. So here's maybe SAT scores, maybe on one part of it. I forget how they keep changing how these SATs are scored, but maybe this is like the math score. And so we can see this histogram has this kind of nice kind of hill shape, mound shape, bell shape. We say it's symmetrical because if you imagine kind of laying like a smooth curve over that thing, and you imagine kind of splitting that curve right around the middle, and the middle looks like what? The middle actually looks like it's right around 600. And you kind of like folded it right along that middle, folded it right about 600. The two ends of that bell shape would overlap with one another pretty well, wouldn't they? So when you have something called an axis of symmetry, a point where you can fold it and the ends will match up with one another, we call that symmetric. And this, of course, this is a nice example of a histogram. So this is what I was saying. A histogram looks like a bar graph. Really, the big difference is the bars touch one another. A bar graph, traditionally, the bars are separate from one another. In a histogram, the fact that we make the bars touch one another is to kind of show or to denote that this is a continuous numeric variable we're working with. That these are actual values that take place on a continuum, and the actual categories that we're creating, because each bar becomes sort of its own category, the categories that we're creating are a little bit arbitrary in nature, right? That is, this has what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bars. This was picked, I actually think maybe I used R to do this. This was picked by R as kind of the optimal number of bars. But different software programs can compute the the quote optimal number in different ways. So a different software package might decide 11 bars is optimal, and another one might decide 13 bars is optimal. So unlike a qualitative, where we actually have a fixed number of categories, here we have something that's not really categorical, but we're creating these artificial categories for the sake of making these bars. Right, the bars sort of represent categories. So if we look at, it looks like we have a bar from 500 to 550, so that becomes a category. People who scored between 500 and 550 becomes a category. We have a bar that looks like it goes from 550 to 600. So, right, students that score between 550 and 600 becomes a category. The height of the bar tells us how many students fell into that category. So we could see that the bulk of the students kind of scored around 600, and as we move away from 600, we see, right, less and less students getting either of those scores on either end of that bell shape. So if something is not symmetric, it's skewed. This is an example of something called right skewed. It's very steep on the left and tapers out to the right. So there's a couple variables, sort of real life variables that classically follow a right skewed distribution. Salary is maybe the most common one. So it's been shown time and time and time again that salary follows a right skewed distribution. Part of why is what? Because you can't really make less than $0, right? So we have like a little bit of a wall effect, right? We have this invisible wall at 0. But in theory, there's no upper bound on how much a person can make, right? So it kind of smashes against that invisible wall to the left, but just sort of tapers off indefinitely to the right. So the bulk of people, right, are in that large bar, whatever that is. The bulk of people are making what? They're making, I don't know what it is, $30,000, $40,000, $50,000. But then we move one bar over, right? There's substantially less people there, but they're making more money. They're making, say, in the $60,000, $70,000, $80,000 range. And then we move over again, right? There's a smaller bar. There's less people, but these people are making in the $100,000 range. And then we go one more bar over, right? That's in the $150,000 range. And we keep going and going and going. We have these ever-shrinking bars, right? And we keep going and going and going. At some point, we get into the $500,000 range. There's not a lot of people that make $500,000, but there's certainly some, right? And we go even further and further. We get into the millions. There's not a lot of people that are making $5 million, but there's some. Some athletes, right, in the Philadelphia area are making that much money. I don't know, maybe some bankers or CEOs. Again, not a lot of people, but certainly some people are making, who knows, maybe as much as 10, 20, 30 million dollars. And that creates this kind of this tapering tail that kind of goes on and on and on, right, into the multi-millions. Incidentally, not just salaries, but like for a large geographical area, the value of a home follows like the same sort of right skew distribution that home values. And that actually kind of in some way kind of would follow right from salaries, right? Because, right, again, we're going to have a lot of people. They have the same basic shape, right? We have the bulk of people that were making $50,000. Well, they're living in whatever the value of a home is that you can buy for $50,000. And then a lot less people are living in these $100,000 homes, and even fewer people are living in these $150,000 homes, and it tapers and tapers and tapers. There's not a lot of people living in $20 million mansions, but there's some. And hence we have that right skewed distribution. Here's an example of a left skewed distribution. So now it's kind of steep on the right and tapers off to the left. So the kind of like the textbook example, I think that you see a lot more right skew in sort of nature and in real life, and not a lot of left skew. I personally haven't seen a lot of left skewed distributions in practice. The kind of classic example you'll see in a textbook, not really sure how true it is or isn't, is like the lifetime of a light bulb. So textbooks often say that like lifetimes of light bulbs, even like more generally lifetimes of like electrical components, follow a left skewed distribution. So if that was true, we would maybe have this like, let's think of, instead of 0.8, let's think of that as maybe like 800. So whatever, 800 hours. Maybe like most light bulbs will last 800 hours. Maybe that's what it even says on the package, is that your light bulb should last 800 hours. And some of them last more than 800, but there becomes kind of like this hard bound, like no more than none of them seem to last more than 100 hours. However, right, we do have them sort of tapering off to the left. So, right, some of them last 60 hours or 600, some of them last 400, some of them last 200. Keeps tapering and tapering and tapering. Doesn't happen every so often, but probably some of us have examples where we put a brand new light bulb in our thing, we turned it on, and it just like burned out in like a minute or two. Doesn't happen a lot, but I guess it can happen. And so a claim, I don't think it's as intuitive as the salary one, but a claim is that lifetime electrical components follow this kind of left skew distribution. At the very least, we can hopefully like get a sense of what the shape is, even if it's harder to imagine it in practice. Some people actually say, actually one example that kind of makes sense is, I've seen this one in a textbook. If you made a histogram of like students in a class for like an easy test, right? So an easy test actually this, we could think of this as percentages, can't we? So an easy test, maybe most of the students get around 80%. And we actually, now we have like an artificial wall to the right, don't we? Because you can't get more than 100%. So it creates a little bit of a smushing effect to the right. However, we have this sort of tapering effect to the left. Because, right, you could get much, much lower than 80%. You can get 60%, 40%, 20%. There's not a lot of students that got only 10%, but one or two of them that just for whatever reason, just didn't study at all and ended up doing very, very poorly on that test. Here's like an example of a bimodal distribution. So an example of this, and I've never figured out why, but supposedly, if you were to go around Westchester University, and if you were to take a sample of a bunch of Westchester students and measure their height, and make a histogram of that height, it would look like this. So bimodal means that it has two peaks. So we think of the modes as these peaks. So bimodal just means two different peaks. Why do you think a histogram of student heights would look like that? It doesn't make any sense to me. Do you have any ideas? That's a pickle. It's a real dumdinger. Oh, that's your idea? So you're telling me you think that the reason it looks like a bimodal distribution is because that you have male students and female students, and that there's certainly exceptions, but in general, on average, males tend to be taller than females. So maybe, aha, I think you're onto something. Maybe what we're observing when we see a bimodal histogram is that there's actually sort of two different subpopulations going on in our larger population, right? And so maybe if we make a histogram and we see something like this, that's telling us that there's two sort of distinct groups in our population that should perhaps be analyzed separately. In this case, right, we have males and females, and right, we probably would report the average height of males and the average height of females separately, rather than some average height of a student. Yeah, well done. The last shape is something like this. So a perfectly uniform distribution is where all of the bars would have the exact same height. Now, we're not going to observe something like that in nature. What we would see instead is something that's roughly uniform, and where the bars are all kind of roughly the same height. A lot of games of chance, I guess, kind of fall into this framework. So imagine that you have a six-sided die. You roll it 6,000 times and you made a histogram. So you have a bar for how many ones you roll and a bar for how many twos you roll and threes and so on. And again, six-sided die, you roll it 6,000 times. You're going to expect about 1,000 ones, right? and about 1,000 twos and about 1,000 threes. And you'll probably get a little bit more for some and a little bit less for others, but the bars, all 6 bars, will probably be very close to one another in height, and so we might say that that's an example of a uniform distribution. Now, making these graphs is pretty easy. I think in our last lecture, or very close to our last lecture of Stat 511, you should have seen how to do really, I think, all of these things, even the ones that we skipped, the pie charts and the bar graphs. You should have seen how to make all of these very easily using proc sgplot. So graphical summaries are potent and powerful. It's a theme that we'll develop throughout 512, and so hopefully throughout the class we'll develop an appreciation for their potency. Graphical summaries are powerful because the human eye is really good at looking at pictures. It's sort of evolved in such a way to respond well to pictures. We're good at patterns. We as human beings are good at pattern recognition. So when we put a pattern, we put a graph up there, the human eye is good at it, is good at looking at it, and sort of instantaneously seeing what's going on. There's a lot of truth to the motto, right? A picture is worth 1,000 words, and a graph is maybe worth 1,000 pictures. So I'll leave it to you to do the math as to how many words it would take to get there. That said, there are weaknesses when it comes to graphical summaries, right? Graphical summaries usually only give a rough or subjective feel of notions like center and spread. So if you were to look at those histograms in the previous slides, we probably could have said like roughly what the average height of a male or a female is. We could have said roughly what the average SAT score is. But probably if like all 20 or 30 of us wrote down on a piece of paper what we thought the sort of average or center was for these distributions, we'd probably come up with slightly, very close, but slightly different answers. And this becomes even more so when we try to describe the spread or variability in these distributions, right? That is, it becomes a little bit tougher. Again, we do have a sense of how variable they are, right? Are all the observations spread out or diffuse? Are all the observations close together? But again, it's sort of like a subjective feel. If you tried to write down the description of the spread of, say, that SAT distribution, and another student wrote down theirs, again, your things would probably be similar, but I'd be surprised if they're exactly the same. And so there's a certain amount of arbitrariness. There can be a further level of arbitrariness in terms of our histogram and picking the number of bars or categories. When we're making scatter plots, something we'll talk about at the beginning of 512, when we're making scatter plots and plotting lines on these scatter plots, actually I think we did a little bit of scatter plots and lines in 511, we can actually make the lines look as flat or steep as we like by sort of playing around with the scale of the graph. So again, we have a certain arbitrariness of scale that kind of can distort our picture and make lines look either flatter than they really are or steeper than they really are. And so with all of these kind of these observations, right, a graph is nice, but we're left wanting something more, or perhaps something to combine it with. That is, we're left wanting something a little bit more objective, something a little bit more concrete. And we're gonna actually get that in our next PowerPoint when we look at these more black and white, objective, numerical ways of describing certain attributes of a sample, these numerical descriptive statistics, which is what we'll talk about next.